In this presentation, we're going to consider what happens when two sinusoidal varying functions are not in phase with one another. And we're going to see this as we continue to talk about circuits that are AC circuits. So it's possible that we can have a circuit that has components in it so that the voltage of the source and the current that's coming out of the source are not in phase with one another. Now, everything we've done so far in DC, it's direct current, so there's not this alternating effect. And so when the voltage was a max, the current was a max if you just had a resistor. But if you have, for example, a capacitor or an inductor in a circuit in DC, it's possible that you could have a very large voltage and have a very small current during the charging process of a capacitor or during an energizing part of an inductor. It could be the opposite. So we can definitely have the situation where the voltage and the current are not necessarily maximums at the same time. So here in our first picture, we have oscillating voltage that's sinusoidal, oscillating current that's sinusoidal, and they are in phase. So they both reach their maximum at the same time, they both have a minimum at the same time, and so we say that they're in phase with one another. But it's possible that you can actually have these values so that they are shifted from one another. So in this case, you've got the voltage up here, which is a maximum, and at the time when the voltage is a maximum, it's not the same time that the current is a maximum, because the current is actually a maximum over here at some location. In this particular case, we say that the current leads the voltage because the current in time reaches its maximum value here prior to in time when the voltage reaches its maximum. And it's going to be pretty obvious when we look at this in phasor notation which one leads and which one lags. In this particular picture, the current lags behind the voltage, so I have also these sinusoidal varying functions. So here's where the voltage is a maximum, and in my current doesn't reach a maximum until someplace over here. So my voltage is reading a maximum first, and then my current, so the current is actually lagging behind, or you could say that the voltage leads if you want to think about it that way. So looking at this in terms of the sinusoidal time-varying representation of voltage and current is a little harder to see which one leads, which one lags. It can be very confusing if we're not careful. But if we represent these sinusoidal varying functions in phasor form, it becomes much more clear which one is leading and which one is lagging. So here is one of the previous pictures, and in this particular case, we said that the current leads the voltage, but if I draw these sinusoidal functions in phasor notation, I realize that my current is phase shifted to the left by an angle theta. So when I represent my current, it is a positive angle, some positive angle theta. And my voltage is actually starting off at 0 at time t equal to 0, so its phase angle is 0. And so you can see if I look at this picture and I look at which, is it the current or the voltage that comes first, as this is oscillating around this axis, the current is always ahead of the voltage. And so the current is leading the voltage, and not only can I tell that it's leading, I can tell you that it's leading by an angle here, theta. So suppose that I have two sinusoidal varying functions, and here I have voltage and I have current, and I wanted to sketch these particular waveforms. Now, I did this ahead of time because trying to draw these by hand on the computer screen, I would be making a lot of mistakes. So I used Excel to actually create these pictures ahead of time. But just so that, when you want to do this, you'd have to draw these pictures yourselves. But just to get an idea of how this works, as I drew this voltage supply, I realized that it has a phase angle of 30 degrees, which means that it is shifted to the left by 30 degrees. So I'm looking at this function here for the voltage. The voltage would be 0 over here, sine would be 0, so it actually at time t equal to 0 is here, so it's shifted by 30 degrees. These should actually be dotted lines, but again, it was too difficult to do that using Excel. As I look at the current, I realize that the current is shifted by 40 degrees to the right. So here's my sine function, and that's where it would be 0, sine would be 0, and so if I follow that back, 40 degrees, it actually hits on the axis over here, and so this is what my sine function would look like with a phase shift of negative 40 degrees, or shifted 40 degrees to the right. When I draw these in phasor notation, oh, before I do that, I guess, so what is the phase angle, the phase shift between the voltage supply and the current supply? So I look at where they both would have started at 0, and I see that the difference between those is 70 degrees. So where does this sine angle start compared to where the current sine function, excuse me, and that is 70 degrees. Now if I draw them in phasor notation, I can start by drawing the voltage. So the voltage has a maximum of 20 volts, and it has a phase angle of 30 degrees, which means I would draw it in the counterclockwise direction with respect to the axis, 30 degrees. And I look at that, and it's also, that's the projection, right? So there's where the voltage is at time t equal to 0, and there would be my projection. My current has a maximum value of 18, and it's shifted by minus 40, so I would have to draw it below the axis. And again, here is where the current is at time t equal to 0. That would be the projection right here. And so I can see that the voltage leads the current, and it leads by an angle between these two, which is 70 degrees. So here is actually a picture that was taken from an older textbook. It's basically the same picture that's on the previous page, but we can see it. Here's that 70-degree angle, and here's that same picture that we had in the previous picture. All right, so here's another one. So I have voltage, which is described as 30 cosine omega t plus 20, and then I have the current, which is a sine function. And so in this case, instead of trying to write the voltage as a sine function right away, I can use my representation that we discussed previously with the sine axis and the cosine axis. And I realized that this phasor for the voltage would be drawn with respect to the cosine axis, and it's a positive angle, so I would have to draw that in the counterclockwise direction, 20 degrees, with respect to the cosine axis. So there's my voltage in phasor notation. And then if I draw the current, it would be with respect to the sine axis. It's a positive angle, so it would be drawn with respect to the sine axis in the counterclockwise direction, 70 degrees. So the phase angle between them would be 20 plus 20, since 70 plus 20 is 90. So the phase angle between them would be 40 degrees, and I can see that if I were to keep these in place, they would rotate around at a constant angular speed to represent those sinusoidal varying functions, and the voltage always leads the current. So voltage leads the current by a phase angle of 40 degrees, or you could say that the current lags the voltage by a phase angle of 40 degrees. Okay, so here's another one that we could look at. In this particular case, I have a sine function for the voltage, which has a negative phase angle, phase shift, I guess I should say. And so I would go to my sine axis, and I would have to go below the sine axis because it's the negative direction. I would go in the clockwise direction, 20 degrees with respect to the sine axis. The current, on the other hand, is written as negative sine of the angle omega t plus 50 degrees. So I have to go to the negative sine axis. I have to go, and then I'd have to measure in the counterclockwise direction. So 50 degrees with respect to the negative sine axis here is, and that's 50 degrees. And so I would want to know what is the phase angle between the voltage and the current, which would be this angle right here. So it has to be 180 degrees between sine and negative sine. So 80 is 50 plus the phase angle between them plus 20. So this angle in here has to be 110 degrees. And I would say that the voltage leads the current by a phase angle of 110 degrees. Or you could say that the current lags the voltage by 110 degrees.